Okay. Sir, you can start now.
Okay, thank you. Good afternoon, everyone, and welcome to this MoES webinar series. In this series, various topics of uh, relevant to science and technology and services of atmosphere, ocean, cryosphere, all were covered in previous webinars. And this is the 9th webinar. So I'll be covering the basics of clouds. At the outset, I thank Ministry of Earth Sciences and also our IITM desk team for giving me this opportunity to talk in this webinar series. As we all know, clouds play a crucial role in weather forecasts and warnings. And it is one of the key uncertainties in the study of climate change. So we need to better understand how clouds affect the climate and how a changing climate will affect clouds. Also, clouds play a critical role in the water cycle and shaping the global distribution of water resources. So with this background, I will go to my presentation. Just hold on. So you're able to see the slides now? Yeah. So the today's topic is cloud physics and how clouds form. And I will go to the outline. So the outline of my lecture will be what is cloud and why are we interested, and what are the types of clouds and how cloud forms, and what are the cloud characteristics as we infer from all these advanced observation methods, and how the clouds behave in the perturbed climate system. And at the end, I will cover some of the MoES initiatives for better understanding on cloud processes. So what exactly are clouds? So clouds seems to be simple for common man's perspective. They're just large masses of airborne water that take random shapes in the sky, occasionally dropping some of their water in the on our heads. So in reality, these clouds cover 70% of the Earth and are complicated, and their specific shapes are determined by different physical processes in the atmosphere. So understanding clouds from a climate perspective introduces new and challenging questions. Still, there is limited understanding on several cloud processes, but significant progress has been made during the last century. So the clouds are made up of liquid water, as you all know, in the form of tiny droplets that are so light they are able to remain airborne without being overcome by gravity. Formally speaking, cloud is an aerosol, that is a suspension of one phase of matter in another. The aerosol is nothing but a colloidal system in which the dispersed phase is composed of either solid or liquid particles, and in which the dispersion medium is some gas, usually air. And aerosols are generally very dispersed. So clouds are a type of aerosol that comes into being when the atmosphere becomes supersaturated with respect to water, and cloud particles grow rapidly and become visibly apparent. So why are we interested? Because clouds couple to the water cycle. They are the vessels in which precipitation develops. Also, clouds couple to the radiative balance by reflecting sunlight back to space, which we call albedo effect. And also it traps infrared radiation emitted by the Earth's surface, so known as a greenhouse effect. Clouds also scavenge all the gaseous and particulate materials and return them to the surface. This is known as wet deposition. And the updrafts and downdrafts associated with the clouds largely determine the vertical distribution of trace species, temperature, and moisture. So the hydrologic cycle, so the clouds play a major role in distributing the global distribution of water resources. So this is the Earth annual and global mean energy budget. So if you see about the energy enters the system as shortwave radiation, and the energy leaves as outgoing long wave radiation. So of the incoming solar radiation, approximately 30% is reflected back to space by clouds and atmosphere, and some portion by the reflectivity of surface. Of the 70% solar radiation that is absorbed, some heats the atmosphere itself, but most makes it through the atmosphere, thereby heating the surface, such as oceans and land. The heated surface causes some direct heating of the atmosphere by sensible and latent heat transfer, but it also radiates much energy upwards. So the presence of clouds reduces the amount of shortwave radiation reaching the surface, so thereby cooling, and also contributes, along with the greenhouse gases, to additional IR infrared radiation towards the surface as back radiation. The atmosphere itself radiates most of the energy to space to balance the net solar radiation absorbed by Earth atmosphere system. The planetary albedo depends to a large extent on the extent of cloud cover, which is cloud traction, but it also depends on the optical thickness of those clouds. So clouds are important to consider in all discussions of climate because their albedos can vary widely from less than 10% to more than 90%. Now, moving on to cloud types, traditionally there are 4 basic types of clouds. So these classifications were by Luke Howard, who was a pharmacist and an amateur meteorologist. So he proposed the first classification scheme based on the appearance of clouds. So traditionally there are 4 basic types. Cumulus clouds are clouds with vertical development, stratus or layered clouds, and cirrus is thin wispy clouds of ice, and nimbus means it's rain producing clouds. So today we have 10 types of clouds based on the altitude at which it resides. So low clouds, so below 2 kilometer, stratus, nimbostratus, stratocumulus, and middle clouds, altostratus, altocumulus, between 2 to 6 kilometers, and high clouds, cirrus, cirrostratus, and cirrocumulus. Clouds with vertical development, so it may extend throughout the atmosphere. In tropics, it can extend up to tropopause, which is about 16 to 17 kilometers. So there are cumulus and cumulonimbus clouds. So these are some of the pictures. You can see the clouds with the vertical development, cumulus and cumulonimbus clouds, and the layered clouds. Stratus clouds are like a blanket it covers and it doesn't have a very clear boundary. And the middle level clouds are having prefix. You can notice that there are alto. And upper clouds, high clouds are cirrus, and they appear thin, wispy ice sheets. And so you can see the prefix for high and high and middle level clouds. For high clouds, it's cirrus is a prefix, and the middle level clouds is alto. So these are some of the pictures what we generally see. So cumulus, and there are a lot of photographs. There is a cloud appreciation society, so which gathers a lot of photographs. These are some of the basic clouds, and the clouds even extend up to mesosphere, which are called noctilucent, and even in surface we call it as fog. So now Moving to the satellite climatology, cloud climatology, so which lead to the development of new cloud classification schemes. Here, clouds are classified according to their cloud top temperature, which is measured by infrared sensors, and its optical thickness, which can be readily measured by their visible albedo. Optically thick clouds with the cold tops are readily associated with the precipitation, and high thin clouds can have strong greenhouse effect, whereas low clouds, which are optically thick, are dominated by their albedo effect. So how the cloud forms? So the major requirements for forming a cloud drop is moisture and aerosol, which is condensation nuclei, and cooling. So actually, what is vapor pressure is it indicates the air's total water vapor content, whereas saturation vapor pressure describes how much water vapor is necessary to make the air saturated at any given temperature. So here in the red curve, what you see is saturation vapor pressure at different temperatures, and it can be noted that warmer the air, it can hold more water vapor, and the cold air is generally dry because it can hold only less water vapor. And at saturation, the relative humidity is 100%. So saturation ratio is the vapor pressure to the saturation vapor pressure. So generally, the supersaturation is the saturation ratio minus 1. If it is 0, so it is air is saturated. If this gets higher than 1, it is supersaturated environment, and it is less than 1, it is subsaturated environment. So air becomes supersaturated either by increasing the vapor pressure or by decreasing T. As a rule, it is easier to bring air to saturation by cooling it than it by moistening. Having 100% relative humidity is not sufficient. Tiny airborne particles called condensation nuclei are necessary for water vapor to condense onto. So these particles are extremely small and light, many having a mass less than 1/1,000,000th of a gram. So without them, relative humidities of several 100% would be required for water vapor to condense. So these are some of the condensation nuclei or aerosol particles. You can see dust and pollen and bacteria and sulfate and sea salt, sodium chloride, and from the sand you can get the quartz and iron oxides, and from biomass burning we can get soot type particles. So what are the sources for these aerosols? They are so dust generally comes from desert or even the changes in land use, land cover patterns. The soot and sulfates, nitrates can come from industrial emissions. Also, soot can come from biomass burning emissions. And ocean gives out a lot of sea salt. And the vegetation also can give a organic type of aerosols. So this is the categories of particulate matter found in the atmospheric aerosol. So you can see there are ranging several orders, 9 orders, starting from 1 nanometer to 10 micrometer. The dust can be up to 10 micrometer. And when you go to millimeter size, you can see rain and hails. So what you see here, the electromagnetic radiation, which can be used to sense these particulate material either through scattering techniques or absorption techniques. So next is the primary ways clouds form. Getting water vapor in the atmosphere to condense into clouds is often accomplished by lifting air upwards. The processes that cause air to rise could be localized convection. Here, buoyancy lifts warm air parcels, or orographic lifting. This is a forced lifting along a topographic barrier, and or convergence. Here winds converge and air is forced upwards, and or frontal lifting. Here buoyancy deflects warm air masses over cold air masses. So maybe you can see pictorially here, the convection is, so locally the thermals ascends and get cools, and you can see the scale 5 kilometer, and in topography it ranges up to 150 kilometer, and in the convergence, so it could be 500 kilometers, and around in weather fronts, lifting along weather fronts, so it can go up to 1500 kilometers. So now how the convective cloud forms. So here, convection is a vertical circulation of air. So that occurs when air gets heated from below by the ground. So parcels of air that are warmer than the environment will tend to rise. And when it rises, it expands and cools. So as the air continues to rise, it will cool to the point at which the relative humidity becomes 100%. So this is called the dew point temperature, which occurs at the condensation level. So as they rise, the energy lost by the air molecules causes the air to cool. So this is where the water vapor contained within the air starts to condense into clouds. The phase change of water from vapor to liquid during lifting also releases a huge amount of latent heat into the atmosphere, adding to the convective instability and causes more air to rise. So which in turn condenses more water and releases more heat. So this feedback loop is part of what helps clouds grow, especially the convective clouds. So here what you see is so here in the parcels lose, the temperature decreases at the rate of 9.8 degree or 10 degrees Celsius per kilometer. So from the condensation level, so the rate of decrease is 6 degrees Celsius per kilometer, which is known as saturation adiabatic collapse rate or moist adiabatic collapse rate. So going more detail into stability. So quickly I will say that, so this is the temperature of environment. Here the parcel is going upward adiabatically, so it loses 10 degrees Celsius per every kilometer. So here you can notice that this parcel is cooler than the environment, so it cannot rise. So it will try to sink. So whereas in the absolutely unstable, the environmental lapse rate is 11 degrees Celsius, whereas the parcel, so dry adiabatically it is 10 degrees Celsius per kilometer. So here the atmosphere is absolutely unstable. So the parcel tend to go up. So another condition is conditionally unstable air. So up to condensation level, the air is stable. So later, so it cools at a rate of 6 degrees Celsius per kilometer. So you can see the parcel is warmer than the environmental temperature. So it can rise and can condense. So another thing is the orographic lift. So this is how when the moist air comes and there is an obstacle barrier due to mountains, so it can forcefully ascend and cool and can have heavy rainfall in the windward side of the mountains. And when we see the leeward side, so there is a decrease in rainfall. Generally, it's called a rain shadow region. So the other mechanism is weather fronts. So here, when a warm air mass is advancing towards a colder one, at the boundary between the two, the warm, less dense air is forced to lift upwards and glide over the top of the colder air mass. This forced lifting pulls the air to its dew point and causes clouds to form. Now, so what are their macroscopic and microphysical properties of cloud? Generally, the macroscopic properties, we say what is the fraction of clouds, how much it's covered, and the base and top heights or vertical extension, and suspended water mass, which is also called the liquid water path, and the optical thickness. So how much radiation it can attenuate. In microphysics, so we have what is the cloud droplet number concentration, what is the size, and how the cloud condensation nuclei get activated, and ice nuclei how it can get activated. These are the microphysics. And the microstructure of clouds could vary from different types. So here I'm showing the stratiform versus cumuliform clouds. Stratiform clouds generally will have lower liquid water content and fewer drops, whereas cumuliform clouds will have stronger time development. So from cumulus, so it goes to cumulus congestus, then goes to a deep convection like cumulonimbus. So here drop size spectrum broadens with the time, so that the precipitation processes can take over. So also the maritime versus continental. So clouds developing in over ocean or and over the land are different. So in continental clouds, we have more cloud condensation nuclei, so it can lead to more droplets, and it could be smaller droplets because the water vapor is the same. There are more droplets have to compete for this, and so it cannot go to larger size, and the spectrum is narrower, and it will have more buoyancy here, aerosols and dynamics. So the microphysics of warm clouds, here we will see how the drops get nucleated. So generally for homogeneous nucleation from vapor to directly form a drop, so you need several 100% of supersaturation. So that generally doesn't happen in the atmosphere. So heterogeneously the drop nucleation has to happen here. So what you see here is the relative sizes of liquid hydrometers and aerosol in the atmosphere. So you can see CCN particle, which is about 0.1 micrometer, and haze drop could be 1 micrometer, and cloud drop is 10 micrometer, and drizzle drop is 100 micrometer, and raindrop is to 1 millimeter. So here, if the surface tension between the water and nucleating surface is sufficiently low, the nucleus is said to be wettable, and the water may form a spherical cap on the surface of the particle. So these particles are referred as cloud condensation nuclei. So larger the particle, more likely it is to be a site for drop formation. If the CCN material is soluble in water, the efficacy of nucleation is further enhanced. Thus, the sizes and composition of aerosol particles in a sample of air have a profound effect on cloud droplet size distribution. Same way, the cold clouds, how it gets nucleated, how ice crystals are formed in the cloud. Homogeneous nucleation occurs only at temperatures below -65 degrees Celsius and at supersaturation about 1000%, which is also again very unlikely. So the ice forms through different mechanisms as listed here. So deposition nucleation. So it takes place when vapor is directly deposited on ice nuclei when the surrounding air is supersaturated with respect to ice. And condensation freezing, which water condenses onto the surface of ice nuclei to form a supercooled droplet and freezes subsequently. And contact freezing is freezing of supercooled droplet upon contact with the ice nuclei. And immersion freezing is ice nuclei become immersed inside a supercooled droplet, then freezes subsequently. So these are the different ice nucleation mechanisms, and this you can see different types of particles which can get activated at different temperatures, and this is how the ice nuclei in the atmosphere is present. So generally it's a very small subset of aerosol particles. So, and these are some of the observations over Mahabaleshwar at different temperatures. So how we could find the ice nuclei concentration. So the next is, the cumulonimbus clouds is a very famous clouds which you can see where you can see lightning and all these heavy precipitation happens. So one of the primary feature is here the upper portion composed of ice, and which extends and spread out in the shape of smooth fibrous striated anvil. So whereas the lower portion is form of mountain of bulbous tower. So cumulonimbus has a younger developing side and an older glaciated side. So the developing side is characterized by updraft motion. See, at the top of each updraft is a cloud turret, which is 1 to 3 kilometer in horizontal dimension. So within the turret, you can see air overturns in the manner of thermal. So the tallest turret you can see it reached above 0 degrees Celsius and attained sufficient maturity that ice particles can form. So the ice appears first in highly localized regions in the form of small unrimed particles. Then these ice particles then extend vertically through the cloud in strands of ice, which at lower levels in the cloud grow by riming to form graupels. The strong updraft velocities in the cumulonimbus favors high condensation rates. So next, this is the precipitating cloud systems. So you can see the mesoscale convective systems. Generally, these cumulonimbus clouds often occur in large groups and complexes, of which individual and lines of cumulonimbus are building blocks. These MCS represent the largest member of the family of convective clouds. They account for a large portion of Earth's cloud cover and precipitation. The patterns of wind and weather associated with them are important local phenomena that often must be forecast on short time scales. So here you can see MCS observed over Odisha in last year, 2019. This is INSAT 3D imager, brightness temperature at 10.8 micrometer. So you can see how the MCS evolves. So then some of the MCS in the tropics also evolve into intense tropical cyclones. So they take a quasi-circular form taken by the upper level cloud shield, which typically surrounds the cloud-free eye in the center of the cyclone. Upper level clouds are also seen to be diverging anticyclonically outward from the center of the storm, while low clouds are spiraling cyclonically toward the storm center. And this is the recent one. So we have been observing last few days, Nisarga. Generally, we classify depression as winds less than 17 meters per second, and storm, the peak wind could be 18 to 32 meters per second, and severe cyclone could be 33 meters per second or more. So it's about 118 kilometer per hour. So generally, the tropical cyclones originate over oceans. So their primary energy source is the latent heat of water vapor in the atmospheric boundary layer, which is released when the air rises out of the boundary layer in deep clouds. And these tropical cyclones nearly always form over regions where the sea surface temperature exceeds 26.5 degrees Celsius. So More on precipitation and precipitation processes will be covered later in a separate webinar by my colleagues. So now next move on to what happens to the clouds in the perturbed climate system. So in this picture, if you see, the unperturbed cloud has larger droplets and fewer number, whereas the polluted cloud can have more number of smaller droplets. So this could increase the reflectivity of clouds. So this is known as cloud albedo effect. So which can cool the Earth's surface. So the next thing is that if these droplets are small and the probability of colliding and coalescing into larger droplets gets reduced. So it doesn't tend to form into drizzle droplets, so that drizzle gets suppressed. And drizzle gets suppressed, and the cloud will tend to live longer time, and even it can extend into vertically. So cloud lifetime gets enhanced. And also these condensation nuclei are of strongly absorbing type of particles, so it can even inhibit the growth of cloud. And so this is the one of the largest uncertainty in climate forcing, which is called indirect effect of aerosols on clouds. So MoES initiatives for better understanding on clouds and its interaction with the environment. So MoES implemented several of these projects in last 10 years. So CAIPEX, which is Cloud Aerosol Interaction and Precipitation Enhancement Experiment. So which is an airborne experiment going into the clouds and understanding the vertical profiles of clouds and how it interacts with the aerosols. So then we also set up a high altitude cloud physics laboratory at Mahabaleshwar in Western Ghats. So here we can have warm clouds coming close to surface, and so it could be monitored how the clouds are getting altered by environment. And also weather radar network by India Meteorological Department. It spaced out several radars in the continent, so mainly along the eastern and western coast. So it immensely helpful for cyclone warning and all. Then we also have a lightning location network, so which gives the alert to the people on lightning, where it can occur and how it can propagate. And one of the new project which is under development is atmospheric research testbed in core monsoon zone in central India. So in CAIPEX, so what we did, what was done is that with aircraft, instrumented aircraft, so cloud properties were observed in different regions of India, and how it how the cloud properties were varying at different heights. Advantages of the aircraft is that you can take profile measurements, how these microphysical properties can vary with height inside the cloud. So only aircraft can do by measuring inside the clouds. So these are the instrumented aircrafts used in. So there were further experiments. Maybe in the later lectures it will be covered. And these are some of the probes, mainly based on the optical scattering method. This is cloud droplet probe, and to understand the ice crystals, you can even image inside the cloud. So what type of ice crystals are prevailing in the colder portion of the clouds, and you can also measure the cloud condensation nuclei and the aerosol particles and liquid water content probe and the meteorological parameters. from the aircraft. And one of the interesting thing you can notice is the vertical profiles of cloud droplet size distribution observed in continental and maritime clouds. So these are drop size distribution at different vertical levels. You can see from 4,500 meter to 7,500 meter. So you can see still, even at the depth of 3 kilometers, the clouds are still, drop size distribution is still narrow. Whereas in the maritime clouds, you can see the cloud's base is from 790 meters to 3.3 kilometer. So you can see even within that this depth, the drop size distribution broadened. So, so there are high chances of creating bomb rain. So in the ice phase, you can notice like what kind of above 5 kilometer, because the dust aerosol could act as a potential ice nuclei at temperatures lower than minus 14 degrees Celsius. So you can see at different heights from 6 kilometer to 7.5 kilometer, there are different variety of ice crystals are noted. So next thing is like, so in addition to aircraft measurements, so we can also have cloud measurements from ground, especially at orographic sites. So this is the high altitude cloud physics laboratory set up at Mahabaleshwar. So here, so why did we establish here? So it could be it's a natural laboratory wherein warm orographic clouds form due to forced condensation, and it can float close to surface and interact with the aerosols and environment near surface. Also, orographic precipitation, which is a source for hydrological cycle, needs better understanding. So increase in anthropogenic emissions and land use land cover changes play a role in modifying the microphysical processes in clouds and precipitation. So you can see clearly here, so all these orographic regions have heavy precipitation. And these are the instruments deployed at Cloud Physics Lab. So this is a Cloud Probe. It is similar to the one used in aircraft, but you have to have a slightly different arrangement to draw the cloudy air, and using optical scattering, you can size and count the number of droplets, and you can observe the liquid water content of clouds. And the microwave radiometer, using the passive emissions from the atmosphere due to water vapor, you can get the water vapor, cloud liquid water content, and the temperature profile. And this is a whole sky imager from which you can keep monitoring the type of clouds and cloud fraction. And this is the ice nuclei spectrometer. So you can create conditions such as very low temperatures, minus 25 degrees Celsius to minus 35 degrees Celsius. And you can increase the ice supersaturation and see what fraction of ambient particles are getting converted into ice nuclei. And ceilometer will give the cloud base heights. So also there are remote sensing systems like radar. So radars are, here we have two types of radars. One is very sensitive to clouds, so which can see the vertical structure of clouds and up to range of 25 kilometer. And the other is a precipitating radar, which is X-band radar. So it also can give a three-dimensional structure of precipitating clouds in about 125 kilometer range. So these are the research areas currently we are working in this high altitude cloud physics laboratory. Cloud macro and microphysics measurements, cloud aerosol interactions, aerosol and CCN. How when you know the aerosols, so how do you estimate the cloud condensation nuclei and see whether the observed CCN is matching with your estimated CCN, and ice nuclei measurements, and trying to parameterize, because so this is one of the important thing which can improve our current modeling systems, and to study aerosol hygroscopicity, which is water uptake of aerosols and its different chemical mixing in CCN activation process, and what is the role of secondary organic aerosol in cloud condensation nuclei activation. Also trying to understand the vertical structure and morphology with radars, and understanding the orographic cloud and precipitation processes. So it is actually serving as a good test bed for understanding orographic precipitation processes and warm cloud microphysics and aerosol cloud interactions. These are some of the samples you can see from whole sky imager. So you can see the different types of clouds observed during daytime. So you can also record the cloud types in the night because it has an IR camera. So if you look at the cloud fraction in different seasons, so you will see in winter you have very low cloud fraction going up. In pre-monsoon, you have cloud fraction gets increased, and in monsoon you can have almost cloud cover in this region about 90% of the 90% of the time. This cloud fraction is about 95%. With a passive microbial radiometer, you can monitor the integrated vapor and also integrated cloud liquid. So what you see here, the blue line is integrated vapor, which will be in centimeter. This means that you bring entire water vapor vertically, and if you see, it will be about few centimeters. So in dry seasons, you will see 1 to 2 centimeters, and in monsoon, you can see up to 4 to 5 centimeters. And what you see in the brown color, which is liquid, it is cloud liquid water. If you integrate the amount of liquid water in the cloud from base to top of the cloud, so you get the amount of liquid water, which is in millimeters. So you can see how it varies during monsoon. So also, this is independently the rainfall observed. So you can see, so we can try to see how the vapor gets converted into cloud liquid and how much rain we observe here. So this is the cloud droplet probe, which I mentioned. So you can get the cloud droplet size distribution instantaneously. So this is a short time lapse when the clouds enter into this probe, how the drop size distribution varies, and what is the liquid water content information. So the long-term data sets are being understood now. So this is the average cloud drop size distribution in one of the recent monsoon. And the CCN, how we measure is, so it has a CCN counter, so which you create supersaturation at different supersaturations from 0.2 to 1% and try to measure what fraction of aerosol getting activated as cloud condensation nuclei. So this is the supersaturation spectra. This is the amount of aerosol we observe in different seasons and what fraction of these aerosols getting activated as cloud condensation nuclei at different supersaturation. Then, if you understand these processes, if you know aerosol information, so we'll be able to simplify how do we estimate the cloud condensation nuclei in different regions. So this is ice nucleating particles and aerosol concentration. So this is some of the recent work which is being undertaken in this lab. So try to measure the ice nuclei at different cold temperatures. So what you can notice is, so this shaded portion is a time where there was a dust storm. So whenever there is a dust storm, you can see the more dust particles, which could be very efficient ice nuclei. And when you enter into monsoon, So you see very few ice nuclei in the surface, near surface. So radar is a very powerful tool to map internal structure of both precipitating and non-precipitating clouds. So no single radar is able to observe both. Centimeter wavelength radars are good for detecting and deriving precipitation, whereas to detect clouds, so we need more sensitive millimeter wavelength radars, and to detect and map the structures of non-precipitating low, middle, and high clouds. Whereas this has an disadvantage that it can get attenuated in heavy rain conditions. So this is a schematic of a cloud population and how each component of the population might be observed by radar. So you can see the anvil clouds. So you need to only the millimeter wavelength radars can see. So whereas the precipitation, air motions, and these things can be observed by centimeter wavelength radars. So again, if you want to see the cumulus clouds, developing cumulus, so you need to have millimeter wavelength radars. So I'll show quickly how the precipitation radar, difference between precipitation radar and cloud radar. So I'm just swapping between these two. So this is precipitation radar. So it cannot see the anvil clouds, and whereas the cloud radar can see the anvil thin clouds also it can see because it's highly sensitive, and so it works in the millimeter wavelength range. And this is one of the strong case we observed about 16 kilometers with the cloud radar. So this is a position at which radar lies, and so you are able to see about 25 kilometer range, and this is one big one big cumulonimbus clouds. You can see in these portions there are ice particles already forming, and there are precipitation. So with the radar, you can see the different phases of clouds. So the lower portion up to 0 degrees Celsius, so clouds are called warm clouds, and above which there will be supercooled droplets. So this is called the mixed phase clouds, and at the very low temperatures and very high heights, so you can see purely it's a glaciated type of clouds. So with the help of polarimetric parameters, you can see these melting layer, or in radar we call bright band. You can see the transition between the ice phase to liquid phase. So there are some advantages with the polarization measurements in the cloud, in the radars. So we were mentioning about the orographic clouds. So in this map, what you see here in the color is the topography. So 1200 meter red indicates 1200 meter height. So this is the Western Ghats, and the Mahabaleshwar is somewhere located here. So the clouds, you can see how the orographic clouds are moving, and in the leeward side you can see some of them get dissipated. And we can also see, so at what points these the storms get initiated. So here the convection initiation is defined as the first time occurrence of a convective cell with reflectivity of about 35 dBc. So these were triggered upstream of mountain barrier, so intensified in upslope. That is the windward slope of mountains, and moved over the leeward side. So significant orographic influence on initiation and sustenance of convective activity can be noticed. So this is from one season data. You can see how these cloud types could be classified based on these convective cell types. So So this is the orographic region. So you can see most of the frequency of occurrence is many over the orographic region. And in the leeward side, you can see the deep convection clouds, congestous and deep convective clouds are more. So this is how the clouds vary with the time during the day. Generally, there is a lead lag relation between congestous when it gets into deep cells. So this indicates shallow to deep cloud transition. So also the radar could see the deep convective storm clearly, and the polarimetric parameters can also give some indication about supercooled liquid prevails in this region and partially frozen hydrometeors lofted by updraft. So during these times, so we also notice the lightning flash density. So these are time variation of lightning flash density observed by lightning location network, which I mentioned earlier. So you can see when these tall ZDR columns are observed, there is a supercooled liquid, and the partially frozen hydrometeors are taken upwards by the updraft motions. So which indicates the lightning activity. This is how the time evolution of storm can be studied. And I mentioned the lightning location network. This institute has set up a network over country. About 80 sensors were installed over the country, and also there is a mobile application, so which could give information about the lightning alert in your region. So next, how these remote sensing helped getting the cloud statistics of different clouds. So initially, we have been working with visible and infrared sensors. So now from 2000, there are active remote sensing systems such as radar and lidar were put into satellites, so it can see the levels of clouds at which clouds. So it lead to better better cloud classification and its location. So this map shows the low clouds with the low bases. Bases less than 3 kilometer and thickness less than 3 kilometer. And this is 3 to 6 kilometer, and bases less than 3 kilometer and greater than thickness is greater than 6 kilometer. So such a detailed classification not only for low clouds, for mid-level clouds and high-level clouds are available now. And with this, the cloud radiative forcing estimates got considerably improved. So when only the passive instruments are used, so you can see. So I'll take some time here. So increasing optical depth means so thin to thick clouds, and increasing height, it's low-level clouds to mid clouds. So with the active sensors like radar and lidar, so we are able to see the multiple layers, deep convective clouds and multiple layers and multiple level of clouds. Sometimes upper level clouds are above the low level clouds, which are not clearly seen by passive satellite sensors. So this helped improving the radiative forcing estimates. You can clearly see. So here the type 5 clouds are showing about minus 60 watts per meter square cooling, but with location of clouds, so it is considerably reduced to minus 40, and it also showed The type 2 clouds are also contributing highly, which is deep convection and multi-layered clouds. So there are several processes takes place in the cloud formation and how it interacts with the environment, aerosols, cloud, and in cloud there are several processes which you can see here. So these processes need to be understood better in each of these regions, especially over tropics. So with this, we also proposed there is a project which is going to come up. It's a research testbed facility. It is a highly focused observational and analytical research effort. So that will compare observations with the model calculations in the interest of accelerating improvements in both observational methodology and in models. So here the focus will be on clouds and convection processes, land atmosphere interactions, and aerosol and radiation. This will help developing and testing the parameterization schemes in weather and climate models by implementing advanced measurements in cold monsoon zone, which is presently lacking. So to summarize, cloud is just air that has been cooled to its dew point. Clouds need condensation nuclei to form. Rising air expands and cools, and sinking air compresses and warms. And whenever plumes of warm air rise into the atmosphere, so this is also known as convection cells or thermals. If these convection cells rise high enough, they may cool the air to the dew point. So this forms cumuliform clouds. So low levels are tend to cool, and high level clouds are warming the Earth atmosphere system. And observation of vertical structure of clouds is essential for unraveling these opposing feedbacks of high and low clouds. Major breakthroughs in measurement capabilities and theoretical understanding have improved our understanding on the characteristics of CCN and ice nucleating particles and their role in shaping cloud microphysical properties. So despite these advances, not all their impacts on cloud formation and evolution have been resolved. So with this, I will stop here, and I thank all of you for patiently listening, and I will take up some questions. Thank you.
Thank you, Dr. Pandithurai, for a very basic talk about cloud and taking us through the state-of-the-art facilities that MoES has set up for studying it. So we have some questions from the audience. There are overwhelming number of questions, but I could only accommodate a few because of time constraints. So it's in your chat window. So kindly read the question and answer.
Okay, the one question is, in the beginning of the month, May this year, there was significant raining, which lasted few days in Lucknow and nearby areas. Could this be because of decrease of dust particles? Okay, so this is a question. I don't think it is due to decrease of dust particles. So actually the major ingredient should be the moisture. So moisture should be available. Then only the presence of dust will help in forming clouds and raining. Yeah, so the next question is, cloud formation are mostly occur at night or early morning in the month of April and May from ceilometer observations and data. Why? So generally the cloud formation occurs in the afternoon hours. So because the convection is strong. So your question is that you are saying occur at night. So it's not always true. So it based on the stability and the moisture and the water vapor. So I'll move on to the next question. Can we differentiate the continental and maritime clouds except microphysically? For example, based on physical properties of clouds, can we differentiate continental and maritime clouds? So generally, the maritime clouds are stratocumulus type of clouds. So it so continental clouds, because you have more condensation nuclei, so it tends to grow vertically higher. Okay, the next question is, can we distinguish and estimate the contribution of various CCN nuclei, especially for marine cloud formation? As of now, we cannot clearly distinguish the contribution of individual CCM nuclei. Generally, in the marine environment, we have sea salt and DMS emissions, dimethyl sulfide emissions, so which also gives into the sulfide particles. So we cannot clearly distinguish the contribution of CCN nuclei to the clouds. Can we relate the relation between clouds and trees? Generally, the area having more amount of trees, having more rainfall, what is the reason behind that? Okay, this is an interesting question. So actually, the trees also can emit volatile organic compounds. So this is generally known as biogenic volatile organic compounds. So these volatile organic compounds also can get from vapor to particle form, and it can also contribute to a large number of condensation nuclei. On even the leaf fragments and pollens also can act as a efficient cloud condensation nuclei. Is there any parameters through which we can estimate the CCN contribution, like sulfate, carbonaceous, mineral dust, from marine cloud formation? Yeah, there are a lot of studies. The laboratory studies are going on. So what they do is they simulate the marine environment and see from that what type of particles get emitted, how potentially it acts as a cloud condensation nuclei. There are some laboratory studies, a big setup people are working on to see the marine algae and all these could be in laboratory, could be simulated and see what each of them contribute to cloud condensation nuclei. Yeah, so these are the questions I could see in my chat window. So with this, I sincerely thank all of you and thank Ministry of Earth Sciences and our IITM IT team, and also Dr. Vinu Valsala, who's a desk who's coordinating this webinar series. So thank you very much.
Thank you, Dr. Pandithurai. Thank you very much. Computer time, we can go now offline.
Thank you.